Welcome back to AI Paper Podcasts. Today we are looking at WideSeek-R1, exploring with scaling for broad information seeking via multi-agent reinforcement learning. This one is by Zelai Xu and the team from Tsinghua University and Infinigence AI.
And this paper, it's a direct challenge to the current big trend, which is depth scaling. Models like DeepSeek-R1, O1, they use these super long chains of thought to solve a single, really complex problem. That's depth.
And this paper says, hold on, there's another way. They propose with scaling. So instead of one agent thinking for ages, you have a lead agent that orchestrates a whole team of parallel subagents. And the headline result, it's pretty staggering. Their model, WideSeek-R1, is only 4 billion parameters.
Which is tiny by today's standards.
Really small. Yet on their WideSearch benchmark, it hits an item F1 score of 40.0%. Now, that number might not mean much in isolation, but it's comparable to the single-agent DeepSeek-R1, the 671B model.
Which is what, nearly 170 times larger?
Exactly. And the mechanism is this hierarchical multi-agent reinforcement learning framework. The lead agent delegates, the sub-agents work in totally isolated contexts, and you avoid all that memory pollution. It's a huge efficiency play.
It really is. It could redefine how we approach scaling for a whole class of problems.
Okay, let's unpack that. For everyone listening, we're all, very familiar with the scaling laws we've been living by. More parameters, more data, and now more test time compute with things like chain of thought.
Right. That's the System 2 thinking model. You give an LLM a really hard math problem, and it just grinds away, generating thousands of tokens of reasoning to get to the answer. And that's depth scaling. It works incredibly well for things like logic, for coding, math.
But the authors here point out a different kind of problem where that whole approach just hits a wall.
They call it broad information seeking.
Okay, what does that mean exactly?
So think of a query like, find the founding year and the location for all Ivy League universities. It's not a deep logic puzzle, right? You don't need to reason for 1,000 steps. You just need to fetch a few specific attributes for, 8, 10, 50 different things.
And if you just throw a standard, a deep model at that task, even a really big one, it starts to fail. Why?
Two big reasons. The first one is what they call context pollution. So imagine you're a single agent doing this sequentially. You search for Harvard, get the info, great. Then you search for Yale, get that info. By the time you get to, say, Dartmouth, your context window is absolutely stuffed with irrelevant tokens about Harvard and Yale.
And the attention mechanism just starts to get confused.
Precisely. The model loses focus. It might start hallucinating Princeton's founding year when you're asking about Cornell. The paper shows it pretty clearly. Performance just degrades as you add more items to the list. The model gets confused by its own notes.
And the second failure is just, it's slow.
Yeah, sequential slowness. It's just simple physics. If you have to look up 50 things one by one, you're stuck in serial. You're just wasting wall clock time.
So WideSeek-R1's whole proposal is to shift our focus, move away from individual competence, just making one model smarter, toward organizational capability.
I love that phrase. It's perfect.
Yeah.
You're not treating the LLM as a lone genius anymore. You're treating it as a manager.
Let's get into the system architecture, because for all the engineers listening, this is where it gets really interesting. They're not just, prompting a model to act like a manager. It's an actual architectural choice.
It is. It's a hierarchical structure. You have a lead agent and you have subagents. And what's really important is that they all share the same underlying model weights. It's the Qwen3-4B backbone for all of them.
So it's the same brain, just wearing different hats.
Exactly. But they operate with different system prompts, and this is crucial, different sets of tools. The lead agent is just the orchestrator. Its prompt is all about task decomposition. And it has exactly one tool it can use, called subagent.
So it can't browse the web itself?
No, absolutely not. That's a hard constraint.
Yeah.
If the lead agent started browsing, it would pollute its own context. Its only job is to maintain a clean, high-level view of the task, break it down, and delegate.
And then it just waits.
It goes idle. It waits for the subagents to report back.
Okay, so tell us about the subagents. They're the ones doing the actual work.
They're the workers, yeah. They get a very specific, narrow prompt from the lead agent, and they have the external tools. They get a search tool to find URLs and snippets, and an access tool to read the content of a page.
And this is the detail that really makes it all work. Isolated contexts.
This is the width in width scaling. It's the core idea. Each subagent is its own little process. Subagent A, looking for Harvard's data, never ever sees the mess that subagent B is making while looking for Yale's.
So there is absolutely zero cross-contamination.
None whatsoever. The noise from the first search can't possibly degrade the accuracy of the 10th. In their experiments, they run up to 10 of these in parallel per turn. They do their work, find the answer, and report only that clean result back to the lead agent.
Who then takes all those clean results and synthesizes them.
Exactly. Or if a subagent comes back with, couldn't find it, the lead can decide to loop again, maybe rephrase the question and send out another subagent. It's a classic rollout, just in parallel.
Now, a lot of us have tried to build systems like this, right? Using things like AutoGen or LangChain. You write some Python, define your agents. But the paper argues those static, handcrafted workflows are brittle. WideSeek is different because it's trained end-to-end.
And this is where it gets really deep into the weeds. They use multi-agent reinforcement learning, or MARL.
Which is notoriously difficult. I mean, the credit assignment problem alone is a nightmare.
It's the classic problem, right? The team get the final answer wrong. So who's to blame? Was it the lead agent for writing a bad subtask? Was it subagent 3 for hallucinating? Or subagent 7 for just failing to use the search tool right? It's a mess.
A noisy gradient problem.
Totally. So to solve this, they adapted an algorithm called GRPO group relative policy optimization.
We saw GRPO and DeepSeek-R1 for their math reasoning. So how does it apply to a multi-agent setup?
They came up with something they call multi-agent advantage assignment. And what it does is basically it computes the reward based only on the final answer.
A group grade. You all pass or you all fail together.
That's it. If the final answer is correct, the entire group, the lead, every single subagent, every token they all generated gets a positive reward signal.
But doesn't that encourage freeloading? I mean, what if 9 agents do perfect work, one messes up, but the lead filters out the bad result and gets the answer right anyway? The bad agent still gets rewarded.
For that one sample, yes. But RL works on averages, over thousands and thousands of training steps. Statistically, that bad agent is going to drag the group's score down more often than not. The gradient will eventually find and penalize that bad behavior. It's a really clever way to avoid reward hacking.
They also talked about a stabilization technique, dual-level advantage reweighting. This felt really key to making the training actually work.
Oh, it's critical. It works at 2 levels. You have the token level and the agent level.
Let's do the agent level first, because that one seemed almost counterintuitive to me.
So the lead agent can choose to call, say, 2 subagents, or it can call 10. Now, if you think about how the gradient gets updated, a rollout with 10 agents is going to generate way more tokens than a rollout with 2.
Which means it has a much bigger impact on the loss function.
Exactly. So if you don't correct for that, the model just learns a dumb heuristic. More agents, stronger signal. It would just spam the maximum number of subagents every single time, even if the query only needed 1.
So they normalize by the number of agents.
They average the advantage across the agents. This reweighting basically tells the model, hey, only add more agents if it actually improves the final reward. It forces the model to be efficient.
And the token level is a similar idea.
Same concept.
Yeah.
Some agents might write these long, verbose chains of thought. Others might be super concise. You don't want the verbose agents to dominate the learning just because they produce more tokens. So again, you normalize, this time, by the number of tokens each agent generated.
So it's all about making sure every agent's contribution is weighted fairly, no matter how much they talk or how big the team is.
Precisely. The paper says without this, the training just diverges. It's that important.
Of course, to train this, they couldn't use off-the-shelf datasets. Something like Hotpot QA is all about depth. Who is the maternal grandfather of the director of the movie Titanic? That's a deep multi-hot problem.
Right. WideSeek needs width problems. List the population and capital city of all G20 countries. They had to build their own dataset.
And the pipeline for creating this WideSearch benchmark was pretty smart.
Yeah, it was a fully automated 3-stage pipeline. Stage 1, query generation. They used an LLM to rewrite user intents into these structured, schema-constrained queries.
Forcing it to ask for a table with specific columns.
Exactly. Generate a table with columns for rank, country, and population, for example. And they made sure the target number of rows was between 10 and 50, so it's guaranteed to be broad.
Okay, then stage 2, answer generation.
They used a powerful teacher model, Gemini 1.5 Pro, to generate the actual answers. But, and this is the key quality step, they made it generate 2 completely independent answers for every single query.
For consistency checking.
That's stage 3, filtering. They compared the 2 answers cell by cell. If the match rate was below 90%, they just threw the data point out.
Because if a model that powerful can't reliably get the same answer twice, the question is probably just too ambiguous.
Exactly. It's a great way to ensure high-quality ground truth. They ended up with about 20,000 of these training samples, creating a whole curriculum for teaching with.
So let's get to the results. We already teased the 40.0% F1 score on WideSearch.
Right, let's put some context around that. The base model, just Qwen 3.4b running as a single agent, it only got 20.1%.
So the architecture and the MARL training literally doubled the performance of the base model.
Doubled it. And even a bigger 7b model that's specifically tuned for search only hit 15.5%. And other multi-agent frameworks like Agent Flow, which are just prompt engineered, they topped out around 28%.
So that gap, that 12% jump from Agent Flow to WideSeek, that's the proof that the MARL training works.
That's the value add. It proves you can't just prompt your way to good coordination. The agents actually have to learn how to work together.
And then, of course, the big one, the comparison to the 671B parameter DeepSeek-R1.
The David and Goliath number. DeepSeek-R1 scores 41.3%. WideSeek-R1 at 4B scores 40.0%.
It's a statistical tie, basically.
It is. You are getting the performance of a monster data center scale model with something that could, plausibly run on a high-end consumer GPU. It just completely validates their whole hypothesis.
There's a graph in the paper that I think is the real aha moment. The scaling curves.
Oh yeah, that chart is everything. They plot performance against test time compute.
For a depth model, that just means letting it think longer, right? More tokens.
Right, and you see that curve, it goes up for a bit, and then it just flatlines, it hits the context limit and gets confused. It can't improve anymore.
But for WideSeek?
For WideSeek, the x-axis is the number of subagents, 1, then 5, then 10. And the performance curve is just a straight line going up. It doesn't plateau at all in their experiments.
Which implies that if they could scale it to 20 or 50 subagents, the performance would probably just keep climbing.
Theoretically, yes. But here's the really crucial control experiment they ran. They took the untrained base model and just prompted it to act like a manager and spawn agents.
What happened?
The curve went down. The more agents they added, the worse the performance got. The untrained lead agent just got completely overwhelmed by the noise and couldn't synthesize the results.
That's such a critical insight. It proves that with scaling isn't some free lunch. You can't just throw more agents at a problem. You need a manager that has been specifically trained to handle that scale.
Exactly. The MRL training is what teaches the lead agent to manage the coordination overhead. Without it, the whole thing falls apart.
What about generalization? I mean, often when you fine-tune a model so specifically for one task, it kind of forgets how to do anything else.
That's a great question. And surprisingly, no. They tested WideSeek on standard QA benchmarks like Hotpot QA and Trivia QA, and it either maintained or even slightly improved its performance compared to the base model.
How do they manage that?
A date mixing strategy. They didn't just train it on their new WideSearch data. They mix that in with standard deep reasoning data sets. It prevents catastrophic forgetting.
So the model learns when to switch strategies. This is a multi-hop reasoning problem, I'll use depth, versus, this is a list building problem, time to call on the team.
Exactly. It makes it a much more versatile and robust tool.
So let's bring it all together. What are the big implications here for the researchers and engineers listening?
I think the biggest one is democratization. We've been in this cycle where SOTA performance is locked behind labs with, thousands of H100s. This paper shows that for a huge class of very practical problems, you can get competitive performance with a 4B parameter model. You just have to be smart about the architecture.
It also completely changes the latency game.
Oh, massively. Parallelization is huge. If you're building a RAG system and a user asks a question that touches 20 different documents, a sequential agent is going to be painfully slow. WideSeek can process all 20 of those in parallel. The user gets their answer in roughly the time it takes to process just one.
And that's the difference between a product that feels magical and one that feels frustrating.
It really is.
Okay, one final thought before we wrap. The paper stops at 10 subagents, but that scaling curve just keeps going up.
It really opens the door to thinking about genuine swarm intelligence.
Right. What happens at 100 agents? Or 1,000?
We could be heading towards a future where superintelligence isn't one giant monolithic GPT-6. It might be a swarm of 10,000 tiny specialized 1B models, all coordinating in real time.
Like an ant colony. No single ant has the blueprint for the nest, but the colony as a whole builds it perfectly.
Exactly. And WideSeek-R1 is like the first proof of concept that you can use RL to teach that colony how to coordinate effectively. We might be optimizing for the wrong thing by just counting parameters. Maybe the future is about counting agents.
That is a very cool thought to end on. The paper is WideSeek-R1, a must-read if you're working in agents or advanced RAG.
Absolutely.
That's all we have for this episode of AI Paper Podcasts. Thanks for tuning in, and we'll see you for the next deep dive.